So hello and welcome to the e-learning modules that are organized by the European Coastal Flood Awareness System project. My name is Mayalen Irazoki. I work in Mercator Ocean International, and in this module I will introduce you to the concepts of forecasting and hindcasting of marine hazards for coastal flood management. The objectives of this presentation are to first understand the concepts of forecast and hindcast type of predictions, understand the role in a coastal flood awareness system such as ECFAS, explain the approach we have used in ECFAS to tackle this type of predictions, give an overview of their accuracy, and explain their interlinkages. So in ECFAS, the general purpose is to issue warnings of possible near future coastal flooding events that are triggered by marine storms and their impacts. This coastal flooding is driven by high sea levels at the coast induced by these storms, which are denoted extreme coastal total water levels. As such, this presentation focuses on the capability to predict extreme coastal water levels during storms, and the forecast and hindcast concepts will henceforth refer to the prediction of these coastal water levels. Before diving into the concept of forecast and hindcast and the role in the ECFAS system, it is important to understand what processes are involved in the construction of the coastal water levels that drive coastal flooding. So coastal total water levels are composed by the contributions from ocean circulation, steric sea levels, tides, storm surges, and waves. In particular, to compute the wave, so the wave run-up, we would need very high resolution models and information on the beach geometry, which is not available at the European scale targeted by ECFAS. As such, only the wave setup part of the contribution is considered for the ECFAS total water levels, which is parameterized as a percentage of the offshore significant wave height. Unfortunately, due to the fact that wave setup is generally not observed in tide gauges due to their sheltered location, this contribution cannot be directly validated. So to provide timely and meaningful warnings, we need information on three elements related to the coastal water levels. First, we need to know what will be the water levels in the coming days. For this, we need to be able to predict the unobserved near future, which is what we call the forecast. Second, we want to know how far in advance we can predict the coastal flooding. This concept of how far in advance is what is called the lead time of the forecasts. So we not only need to need the forecast, but also we need an understanding of how their skill is affected by the lead time. This aspect is important because it is linked to the time society has to prepare for an identified upcoming flooding event. And third, we want to know how severe, i.e. extreme, will the water levels be and what is the range of extremes we can expect. For example, a 2-meter water level is normal around the English Channel due to the tidal range there, while it is extreme in the Mediterranean coasts. We need a way to measure the severity of the event in order to understand if a warning needs to be issued or not. That is, we need to know what we call the trigger threshold. Additionally, we need to know the range of extreme conditions we can expect in order to build a picture of the possible flood scenarios. For both these elements, we have to rely on our knowledge of the past local water level conditions. To learn about the past, we use what is called a hindcast, which is a reconstruction of the local water levels for years to decades in the observed past. Now, with the concepts of hindcast and forecast clear, we will now introduce the approach and datasets used in ECFAS. Now we will see the workflow followed for the warning component in ECFAS and the role of the forecast and hindcast datasets in it. First, a forecast for the coming 5 days is produced. Here we see the forecasts produced at the Valencia coast during the storm Gloria in January 2020. As we can see, the maximum water level during this event is forecasted to exceed the threshold defined to class the event as extreme. This threshold, as explained, is defined based on the hindcast information of historical local water level conditions. Now, if the threshold is exceeded, the rest of the workflow is triggered. The characteristics of the forecasted event, such as maximum water level and duration, these are evaluated against a catalog of historical flood events in this area, which has been produced using the hindcast as foreseen. Then the historical flood event that best matches the forecasted event characteristics is selected from the catalog, and the associated flood extent and depths are retrieved. As we have seen, forecast and hindcast serve different purposes in our coastal flood awareness system. As such, the model characteristics for forecast and hindcast products often differ. We will give a brief overview of the typical characteristics of such products before introducing the selected forecast and hindcast datasets in ECFAS. So in this table, we summarize the main characteristics that typically differentiate forecasts from hindcasts. One of the main aspects is the time horizon, as forecasts are targeting the prediction of the future in timescales in the order of days, while hindcasts target the reproduction of the past in timescales in the order of decades. Forecasts are produced and updated every few hours or on a daily basis. Given the multiple possible evolutions of the near future, while hindcasts are produced either a single time or updated periodically following model upgrades or temporal upgrades in order to reproduce the single realization of the historical past. Forecast products are therefore focusing on the accurate prediction of single events, such as for raising warnings of upcoming extreme events, while hindcasts focus more on providing an overview of the statistical behavior of the system in order to characterize average conditions, extreme conditions, and their recurrence. Given the different focus and time horizons, forecast models tend to have higher complexity than hindcast models, which is often, although not always, related to higher spatial and temporal resolutions, but also to the inclusion of more physical processes. In terms of assimilation of observations, forecasts use the knowledge of the current observed state to better bound predictions of the unobserved near future, while hindcasts can benefit from past observations throughout their time coverage. The atmospheric forcing datasets follow the nature of the ocean model type they are forcing, with forecast atmospheric products to force ocean forecasts and reanalysis products, that is also past reconstructions of the weather, to force hindcast models. Given the multiple possible trajectories of the near future for both ocean and atmosphere, forecast products show increasing uncertainty with increasing time horizons or lead times, while hindcasts offer a constant uncertainty, which is generally lower than that of the forecasts. So ideally, the same models would be used to produce forecast and hindcast datasets, thereby ensuring in a system like ECFAS the consistency between the future predictions and the flood catalog and thresholds used as benchmark. However, as highlighted on the previous slide, forecast models run on a daily basis with higher resolution in time and space and are therefore computationally costly and generate large data volumes. This is why their temporal coverage is often limited to just a few years. Instead, hindcast type models target multi-decadal coverage and therefore need to compromise on their complexity with often reduced skill for single event predictions in order to reduce computational costs. Therefore, a unique dataset complying with time coverage and accuracy requirements for both hindcasts and forecasts is currently unavailable, and different products, and in this case models, are employed for forecasts and hindcasts in ECFAS. We will describe each and give an overview of the differences we can expect in the representation of water levels. So for the forecasts, the total water levels are produced by extracting and combining data at the coast from the Copernicus Marine Service physical and wave regional operational models, whose spatial coverage is displayed in the figures here on the screen, and which offer altogether pan-European 5-day forecasts at resolutions ranging from 1.5 to 4.5 kilometers at the coast, with hourly outputs, which include also data assimilation and coupling levels between the wave and the ocean systems. For further details on the models, I invite you to visit the Copernicus Marine Service website and catalog through the link displayed here on the screen. Now, for the hindcasts, the historical search levels are produced using the NEU SSL Pan-European Barotropic model. So this is a 2D model. The model has a coastal resolution of 2 to 3 kilometers and employs the ERA 5 atmospheric reanalysis winds and pressure as forcing. Next, the mean sea level variations due to circulation and steric effects are added from the three-dimensional global physical ocean reanalysis product distributed by the Copernicus Marine Service. And furthermore, the regional wave reanalysis products from the Marine Service are also used to compute the wave setup contribution. And finally, the tides computed by the model ECFAS 2014 are added linearly. Since these additions are linear, nonlinear effects between components are missed. And despite having been reported to be substantial in certain areas of the European coasts. The hindcast is produced for the period 2010 to 2020, which is used to produce the flood catalog as well as to derive triggering thresholds for the warning component through extreme value analysis. So before we highlight the way the differences in model configurations for hindcast and forecast affect the water level representation, we briefly explain the main mechanisms through which the different components of the water level interact in a nonlinear way. These nonlinear interactions affect the accuracy of water level estimates computed as a linear superposition of the different components, as it is currently done for the hindcast. This diagram from Idier et al. Indicates the components that interact nonlinearly and the direction of this interaction. One of the main mechanisms is the interaction through variations in depth, since tides, waves, and storm surges strongly depend on depth for their generation, propagation, and/or dissipation. This coupling through depth entails that all components nonlinearly interact with each other, with mean sea level the only component acting one directionally. Additionally, nonlinear interactions are generated through the interaction of currents associated to each component. Lastly, a particular interaction at the air-sea interface is highlighted, where waves affect the sea surface roughness and therefore the effectiveness of the wind to generate surges. With these interactions in mind, we have collected in this table a high-level overview of the main model differences between forecast and hindcast datasets, and to what degree they affect the different drivers of the coastal total water level, and in particular, their extremes. In green, we see those drivers or components strongly impacted by the given modeling setting. In orange, those mildly affected. So we have identified 4 main model differences: the dimensional nature of the model, whether it's 3D or 2D, the explicit inclusion of tides, the coupling between ocean and waves, and the data assimilation, which is the inclusion of observations to steer the model solution towards reality. Since extreme coastal water levels in the context of ECFAS are dominated by storm surges, tides, and wave setup, we have identified those 2 model features that have the largest impact on these components, which is the explicit representation of tides and the coupling with waves. Besides the general higher complexity of the forecast models compared to the hindcast models, the fact that these 2 key processes are missing in the hindcast in ECFAS may result in degraded performance for the hindcast in comparison to the forecast. However, it must be must be noted that the higher complexity in the forecast models entails that model calibration becomes more challenging as the number of drivers of the water level increases. Additionally, given that the Copernicus Marine Service forecast models target a full representation of the ocean physical variables and not uniquely coastal water levels, the NEU hindcast offers more flexibility in tuning the model for this specific purpose. Therefore, in this case, higher complexity doesn't necessarily imply a higher model performance for coastal water levels. All in all, we can expect these differences to trigger inconsistencies at the interface between the forecast and hindcast products, which is discussed later in this presentation. So next, we will look at the performance for both forecasts and hindcasts during extreme water level conditions, which is the focus for ECFAS. For the forecasts, data was only available for a short period of 3 years, and therefore a methodology a bit different to the traditional extreme value analysis had to be chosen in order to make sure that the focus remained on the storm-driven extreme water level events. So a method was developed to detect from observations those extreme events with a significant contribution from the surge, which is used as a proxy for stormy conditions. Here we see the average error of the modeled peak water level during the identified events for each tide gauge location. And that's on the left in meters, and on the right we see the equivalent normalized metric. So what we see is that in average, peak water levels during storms are underpredicted by 13 centimeters, that is 9% in normalized terms. Some regions, those show larger than average errors, such as the southern North Sea, where more events are also identified. Besides the error on the peak water level, the capability of the models to raise a warning in the occurrence of an extreme event is also evaluated. And we find that out of the identified observed events, 80% were flagged independently by the models, and 26% of those flagged were actually false alarms. So overall, we see a good performance with a slight underestimation of the peak magnitudes during extreme events. And while not shown here, we derive similar conclusions for the significant wave height, which is used in ECFAS as a proxy for wave setup. In order to evaluate the impact of the lead time of the forecast on the forecast skill, we look at the evolution of the previously presented metrics, so the peak water level error during storms, for lead times ranging between 0 days and 5 days. Here, the evolution is plotted for 3 regions, regional seas separately. That is the Iberian, Biscay, and Ireland on the left, the Northwest Shelf in the middle, and the Mediterranean on the right. Unfortunately, no past forecast data was available for the other 3 regions, which are the Baltic, the Black Sea, and the Arctic. So we can observe here that in general, performance metrics remain stable up to a forecast lead time of 4 days, meaning that 4 or more days ahead of the storm, the capability to provide accurate forecast decays. And in the context of early warning applications, user surveys have revealed that a lead time of 3 days is the preferred choice by the users. And therefore, the forecast lead time impact observed here should be acceptable for an application such as ECFAS. Now, these results demonstrate here the capability of the models to produce not only accurate, but also timely forecasts in the event of a marine storm. Next, we will evaluate the skill of the hindcast dataset. In order to focus on extreme events over the 10-year period available, we compute performance metrics over those storm surges with values above the 99th percentile at the tide gauge locations. The panels show the distribution of the root mean square error in the top, normalized root mean square error in the middle, and Pearson correlation coefficient in the bottom. for each tide gauge on the left and in a histogram fashion on the right. So what we see is that the root mean square error averages at 18%, with larger errors generally around Northern Europe. And what we see also is that when we linearly include the contributions of tides and mean sea level, the root mean square error for the peak water level is reduced and the correlation is increased, and therefore we improve results when adding these contributions. Overall, and again, we find a satisfactory performance and in the range of the errors that have been reported in literature for models used in forecasting of coastal total water levels at regional scales, such as we have here for the hindcast and forecast. So finally, we highlight the implications of using the two different datasets for the forecast and for the hindcast. Given that the modeling systems, as already explained, are significantly different, we can expect that they present different biases and trends. In ECFAS, the two datasets come together at the trigger component of the system, where the forecasts are evaluated against the threshold derived for the hindcast, from the hindcast, which determines whether a warning should be raised and whether the downstream parts of the system should be activated, that is the flood computation, etc. In order to somewhat calibrate the forecast against the hindcast, a correction is applied to the triggering threshold, ensuring a more consistent activation of the system. Other biases, however, may persist, such as the difference in recurrence of extreme events between the two systems. Since the flood catalog relies on water level ranges and not return periods, the impacts of this inconsistency is somewhat alleviated. So finally, I'd like to point you to other e-learning modules that are directly related to the contents and concepts described in this module, which are the module on thresholds of total water level for triggering coastal flooding and the module on the Pan-European flood map catalog. So thank you very much for your attention. If you have any questions, do not hesitate to contact us in the email displayed in the slide. And again, thank you all and goodbye.